Hey, College Algebra. So we're going to start moving on to the next unit where we talk about rational functions. In this unit, we're going to talk about their asymptotes, real-life examples, and where they're greater than or equal to or less than 0. So for today's lesson, though, we're going to be talking about their asymptotes. How do we find their vertical asymptotes? And how do we find their horizontal asymptotes? And what these asymptotes are points where your rational function will get infinitely close to those lines but never actually touch them. So why are we going to learn about rational functions and their asymptotes anyways? So first off, if you're going to take calculus, learning about rational functions and their asymptotes is a great idea, or a great starting point for understanding the idea of limits of infinity. So here, in the first slide, we're going to get infinitely close to this line but never actually touch it. And so calculus is all about this idea of limits of infinity. So it's a great starting point there. When I was walking through Chicago, I can't remember the name of this building, but I walked past it and it's just really weird looking up on it because it kind of curves towards like the middle of this building. And so it almost looks like the middle of this building is like an asymptote to the outside of it. Kind of cool in architecture. We can also represent how fast the bike is going and how far it will be in an hour using a rational function. We can also describe how ice cubes melt, where they start off as solids and become nothing but liquids as a rational function. We can also even talk about Ice Cube in his career, where he started as a straight-up gangster and then over time has become this family man that everybody loves and appreciates for some reason. Okay, so some examples. Let's go ahead and learn some stuff. Okay, review. Rational functions are represented by this form right here, where we have some function p of x divided by another function q of x. Now, one thing we're going to be hitting on a lot late to this chapter is domain. I know we've hit domain over and over and over again, but remember, it's what you can legally plug into a function. Okay, and the big thing here is that a q of x can never be 0. Now, there's actually going to be a connection between domain and asymptotes. But first, I want to talk about vertical asymptotes and what they look like. So, as I said earlier, asymptotes are a line that the rational function gets super close to touching but never actually touches it. So as you can see here, it's going to get so close but never touch it. And so this vertical line, or this vertical asymptote, is just going to be x equaling to some number c. Remember, when you have x equaling to something, it's a horizontal, or it's a vertical line, not a horizontal. And so you can represent an asymptote or vertical asymptote like this, or where these lines go like this. Both vertical asymptotes. Okay, now let's make a connection between domain and vertical asymptotes. So first, let's actually start by stating the domain of our function. So let's start with number 1. Here, remember, x cannot be -1 and 1. Remember, if we put -1 into x squared here, this would equal 0, and we're dividing by 0, and that's no good. Or if we put 1 into x squared, we'd still get a 0 in our denominator, which is no good. Okay, now that we've stated what our domain is, I want to go ahead and graph this function right here, 3 divided by x squared minus 1. When we graph it, check out where our vertical asymptotes are. They're exactly where our domain can't be. Coincidence? I think not. So, our vertical asymptotes are, I'm actually going to do this in red, x is equal to 1 and x is equal to -1. Those are our vertical asymptotes. Okay, so let's work on 2 now. Here, let's go ahead and factor an x out of our denominator. And so we'll end up having x plus 5 divided by x times x squared plus 1. Okay, so you know that x cannot equal 0 because if we plug 0 into here, our denominator becomes 0, and that's no good. Now, there's nothing we can plug into x squared to make x squared plus 1 0. So our only value that our function can't be is 0. x cannot equal 0. So I'm going to go ahead and pause the video and graph this on a calculator. So when I graph this on a calculator, and I'm going back to y equals right quick, make sure you put in your parentheses right here and right here, or else you'll get some pretty interesting answers. Now, when we graph it, notice how our vertical asymptote is right at where our domain can't be. And so our vertical asymptote is just x is equal to 0. Okay, so what I want you guys to do is work on number 3. Go ahead and pause the video right now. We'll come back together and share our answers. Okay, so I know that the domain can't be 3 or -4. However, this is a tricky problem. Let's go ahead and look at the graph of this. Well, why do we not have a line here at 3 like this? Now, why is that? Okay, so in our function here, we can actually cancel these out. Now, for domain, we still have to state that it can't equal 3, but since we can cross those out, our function ends up being just 1 over x plus 4. And so our only vertical asymptote is when x is equal to -4. Now, I'm going to pull up Wolfram Alpha right quick. And so, as you guys can see here, we have the vertical asymptote at -4, but we just have some hole here. I know you guys can't see it, but there's a hole. And it doesn't mean that since there's a hole, there's a vertical asymptote there. It's just a value that our x cannot legally be. So I hope that was informative for vertical asymptotes, but now I want to move on to horizontal asymptotes. And there are 3 cases where your asymptotes or your horizontal asymptotes are going to be different. So first one's bottom heavy, and then the second one's equal, and then the third one's top heavy, which really isn't a horizontal asymptote, as we're going to find out. And so I want to go ahead and go over each one of these examples. Now, what do I mean by bottom heavy? And so what I mean by bottom heavy is that the degree, the highest exponent in the denominator, is heavier or bigger than the degree or your highest exponent in your numerator, then it's going to be bottom heavy. So 3 is greater than 2, therefore this rational function is bottom heavy. Now, whenever a function's bottom heavy or has a larger exponent in its denominator, then the horizontal asymptote is y equals 0. You're going to get a graph that looks like this. Now, some of you guys might be thinking, well, wait, Mr. Feltham, you said that your horizontal lines never touch your asymptotes, they get infinitely close. Well, as we can clearly see here, they're touching here and touching here. And with horizontal asymptotes, that's okay. You can have them cross. The idea is, as we approach infinity on either sides of our x-axis, that we're going to get infinitely close to this horizontal asymptote, but never touch it. Now, it's okay if we cross, but as we go out to infinity, they should never touch the horizontal asymptote. Okay, now I want to talk about when you have an equal rational function. And so what that means is that your degree in your denominator and your degree in your numerator are equal, or they have the same highest exponent. So here, 2 is equal to 2, and so we can find our horizontal asymptote using this rule for equal horizontals. So if your top degrees are equal, horizontal asymptotes at the quotient of the leading coefficients. What does that mean? So here is our leading coefficient of our numerator, and here is our leading coefficient of our denominator. Now our horizontal asymptote, which is a horizontal line, is just going to equal 3/2. And so as you can see here, 3/2 is a horizontal asymptote. And as these lines go out to infinity, they're going to get very close to our asymptote, but never touch it. Okay, now let's talk about our last case, top-heavy. And this might be one of the more complicated ones, but also one of the more interesting ones. And so this is when your degree in your denominator is less than the one in your numerator, aka your top-heavy. And so 3 is greater than 2, so now we're going to have to deal with these oblique asymptotes. In the beginning, I called them slant asymptotes. I just prefer that term because obviously these guys are at a slant. Now, how do we find what this slant asymptote is? And so we have to use long division to find out what this slant asymptote is. And so for here, we do 2x squared minus 8 divided by x cubed. And so we're still working with polynomial long division. And so we'll have an x up here. And so we'll have, when we do that, minus 2. Oops, I'm sorry, there should be 1/2. Minus 2x squared, or x cubed, plus 8x. Plus 8x, yep. And so here we'll get 0 with a remainder of 8x, because we can't divide 8x anymore because we're working with an x squared. Okay, but now we're working with a remainder. And from last chapter, we weren't really used to having remainders. But in this chapter, it's going to be okay. And so remember, with the rule of long division, we can rewrite f of x. So we can say f of x is equal to 1/2 x plus, and this should be 1/2 x plus the remainder, which is 8x, divided by 2x squared minus 8. Now, this is where it gets a little tricky, but whenever you do these, let's look at this red section. Now, if we're thinking about this idea of infinity, as x gets infinitely big, remember our idea of this bottom heavy. Remember here our horizontal equaled 0. And so as we approach infinity for this f of x right here, this red bit is actually going to be approaching 0 because it is bottom heavy. We have that 2 on the bottom. And so as our function approaches infinity from both sides, it's actually just going to be 1/2 x plus 0, or just 1/2 x. And so our oblique asymptote, or our slant asymptote, is equal to 1/2 x. As you guys can see here, check out our line, has a slope of 1/2. Okay, I realize that might have been a little confusing, so I want to do another example. Let's go ahead and find if, or let's determine if this function has a horizontal, so it should be horizontal, or a slant asymptote. Now here, our degree on the bottom is 3, and it's 4 on top, so it's top heavy. Now top heavy meant that it's going to be one of these long division cases where we try to find a slant asymptote. So let's go ahead and do some long division. And so we set it up by dividing the numerator by the denominator. Okay, so we need to multiply x cubed by 3x. So we'll end up getting minus 3x to the 4th plus 3x cubed plus or minus 3x. So actually, I need another placeholder in here. minus 3x. So we can rewrite this as 3x cubed minus x squared minus 3x and 0. Okay, now we need to make x cubed equal to 3x, so we just added 3. And so we'll have 3x cubed plus 3x squared plus, I'm going to move this over here, plus 3. Okay, so the final thing ends up being that should be positive, 2x squared minus 3x plus 3. Now we can't continue anymore, right, because we have a cubed up here. And so we can say that f of x, or actually h of x in this case, a fancy h of x, is equal to 3x plus 3 plus this guy divided by divisor, x cubed minus x squared plus 1. Okay, but the trick with these remainders is that you're always going to have a bottom heavy case. And so as as h of x approaches infinity, we're just going to be left with 3x plus 3 plus 0, because this green guy is bottom heavy. So trick is that your slant asymptote is always going to be this right here. So here our slant asymptote is 3x plus 3. Okay, so to recap what we just learned, we talked about what vertical, horizontal asymptotes look like, and we also discussed how domain relates to vertical asymptotes. And we talked about how to find each 3 cases with horizontal asymptotes. So, as always, college algebra, stay classy, do your nightly questions, and I'll see you guys next class.